Today's topic is evaluating the limits algebraically or analytically. To evaluate a limit, we're going to try the following techniques. The first one is direct substitution. If it works, that's wonderful, but if it doesn't work, then we have to think about other techniques. If direct substitution gives us a finite number, then that number is the limit. If direct substitution gives us a number over 0, then the function has a vertical asymptote at that point, and the limit may or may not exist. It may be positive infinity or negative infinity or does not exist. You'll have to check both one-sided limits. If we end up with 0 over a number, then the limit is 0 because 0 divided by any number is 0. If we end up with 0 over 0, that's where the fun begins. This is called indeterminate form. Some other examples of indeterminate form are infinity over infinity, infinity times 0, infinity minus infinity. Indeterminate form means we have to do more work. For indeterminate forms, we'll have to try some of the algebra techniques we have learned in the past. For example, factoring and reducing, rationalizing numerator and denominator, simplifying complex fractions, or multiplying out and simplifying. So here's a couple of examples. We're going to be using algebra techniques here for the homework for this section. Only use algebra techniques. Do not use graphical method or numerical method to evaluate the limits. Stick with the algebraic method to evaluate the limits so that we can get the practice of how to evaluate limits algebraically. The first example, like we said earlier, one more time, if we do direct substitution, if direct substitution gives us a finite number, then that is your limit. If it gives you 0 over a number, then 0 is your limit. If it gives you a number over 0, we know there's a vertical asymptote, and if we get 0 over 0, then we do have indeterminate form, and we need to try some algebra techniques. Let's go ahead and try to evaluate these limits. The first one, we have part A, limit x approaches 2, x squared plus x minus 6 divided by x minus 2. First of all, I'm going to go ahead and do substitution. If I plug a 2 in there in the numerator, 4 plus 2 minus 6. And then in the denominator, we have 2 minus 2. This is a 2 minus 2. And that turns out to be 0 over 0. So 0 over 0 is indeterminate form. That means I need to use some factoring techniques, some other ways to simplify and evaluate. So let's go ahead and do that. Limit x approaches 2. Let's go ahead and factor x squared plus x minus 6. The factors would be two numbers multiply to give you negative 6, add up to give you positive 1, are x plus 3, x minus 2 divided by x minus 2. We do have a common factor that we can cancel. Limit x approaches 2, x plus 3 turns out to be, we can just go ahead and plug the 2 in there because this function is continuous at 2 and this limit exists. So sorry, I was going to write 2 plus 3, and that is equal to 5. And that's the limit. If you want, you can verify numerically. You can make a table by picking the values around 2 on the left-hand side and the right-hand side and see what's happening to the limit. Or you can also make a graph of it or look at Desmos, look at Desmos for the graph and see what's happening to the limit as x is getting really, really close to 2. Okay, the y will be getting really, really close to 5. So I'm going to leave that numerical and graphical method for verifying for you. Here we have part B, limit h approaches 0. So if I go ahead and plug h as 0 in there, I will be getting 0 over 0. Again, indeterminate form. That means I need to use some more techniques. Let's see what I can do over here. I'm going to start by foiling this and see where does it take me. Limit h approaches 0. So if I FOIL this, that would be 16 plus 8h plus h squared minus 16 over h. And we do have positive and negative 16 here, and I'm able to factor an h out from the numerator, h plus 8 divided by h. And now we can cancel this, and we're left with limit h approaches 0, h plus 8, which turns out to be 8, and that's my limit. Okay, again, verify numerically and graphically, you will be able to see that this is correct limit. If you have a 0 over 0 form, that means more algebra is needed. Okay, let's check out part C. Limit x approaches 4. So I'm going to start by plugging in. Square root of 4 is 2. 2 minus 2 is 0. 4 minus 4 is 0. 0 over 0 form. That means I need to use some algebra techniques. Limit x approaches 4, I'm going to try to rationalize the numerator. So I'm going to go ahead and multiply both numerator and denominator with x plus 2. Limit x approaches 4, so that leaves me with x minus 4 over x minus 4 square root of x plus 2, because I'm going to be foiling the numerators. When I FOIL first, outer, inner, last, I get x minus 4. Now it looks like I can tackle this easily now. Limit x approaches 4, 1 over square root of x plus 2, and this function is continuous at 4, so I'm able to go ahead and plug the number in. Go ahead and substitute the limit in there. So that would be 1 over square root of 4 plus 2, which is 1 over 4. And that's my limit. Next example, we got part D. For part D, let us see what happens. What kind of form am I dealing with? So if I plug a 0 in there, 1 over 0 minus 2 over 0. 1 over 0 is infinity minus infinity, and that is indeterminate form here again. So indeterminate form means I need to use some more algebra techniques. X approaches 1. So I can get the common denominator. I will have to multiply the first fraction, numerator and denominator, with an x plus 1. So that's what I'm going to do. X plus 1 minus 2 is what I'm left with in the numerator. Limit x approaches 1, x minus 1 over x squared minus 1. Now we can go ahead and factor the denominator. X minus 1 over x plus 1 times x minus 1. And we would be able to cancel this. The remaining function is continuous at x equals 1. It's not continuous at x equals -1, but that's not the point in concern for us. So we are not evaluating the limit at that point. At x equals 1, this function is continuous. There's no trouble with the domain here. So we can go ahead and plug in x as 1, and the limit would be 1/2. All right, next example. So there's lots of examples in this video about evaluating the limits. So let's see, for part F, we have limit x to the 4th minus 1 over x cubed minus 1. So how we can handle this limit? X to the 4th minus 1. Let's go ahead and first plug the number. So I'm getting 0 over 0 form. If I have 0 over 0 form, then that's an indeterminate, so I need to factor more. So this would be x squared plus 1, x squared minus 1 divided by x cubed minus 1. Limit x approaches 1. A lot of factoring required. Limit x approaches 1. So we have x squared plus 1 times x plus 1 times x minus 1. And in the denominator, when we factor x cubed minus 1, that would be x minus 1 times x squared plus x plus 1. Let's go ahead and cancel the common factors. X minus 1 and x minus 1 are gone. So let's see if the remaining function is continuous, and we can just go ahead and plug in the 1 for x's. See if that gives me a finite number. If it does, then that's my limit. So I have 1 plus 1, 1 plus 1 over 1 plus 1 plus 1. I put too many plus signs in the denominator. 1 plus 1 plus 1. Okay, so numerator turns out to be 2 times 2, which is 4, divided by 3. And that turns out to be my limit. Okay. Now we have the next, we are going to look at part H. 1 over x minus 2 minus 4 over x squared minus 4. Again, when x is approaching 2, I have 1 over 0 minus 4 over 0, which is infinity minus infinity, indeterminate form. So that means I need to do more. Limit x approaches 2. I need to do some algebra techniques. And it seems like I can get a common denominator, because x squared minus 4 factors into x plus 2 times x minus 2. These are the factors. So that means I'm going to have to multiply the first fraction with x plus 2, numerator and denominator. So x plus 2 minus 4 is what I'm left with. Limit x approaches 2. x minus 2 over x plus 2, x minus 2, and that's, see, I'm able to cancel this, and the remaining function is continuous at x equals 2. It's not continuous at x equals negative 2. Again, we don't care for that point because that's not where we are evaluating the limit. So 1 over 2 plus 2 is 4. 1/4 is the limit in this case. Let's see a couple more examples. We have 1 over x plus 3 minus 1 over 5. So if I plug in 2 over here, 1 over 5 minus 1 over 5 over 2 minus 2, which is 0 over 0 form. And 0 over 0 is indeterminate form. And that means we need to do more algebra. We need to take care of some algebra here before we can actually come to the conclusion what the limit is. So I'm going to go ahead and simplify the complex fractions. In the numerator, I'm going to get a single fraction. So 5 times x plus 3. I'm multiplying the first fraction, top and bottom, with 5. Second fraction, numerator and denominator, with x plus 3. So 5 minus x minus 3, because a negative sign we distribute in there. And I get limit x approaches 2. 5 minus x minus 3 would be 2 minus x over 5 times x plus 3 divided by x minus 2. So instead of using this division line, I'm using the division symbol. Okay, so limit x approaches 2. 2 minus x, if I can factor a negative out, this is the same thing as x minus 2 because they're opposite of each other. And now I can see the light because I'm able to cancel the x minus 2, and that's what was causing me trouble. That's what was giving me 0 in the denominator. I can go ahead and plug in the 2 in the for x now. 5 times 2 plus 3. It turns out to be negative 1 over 25, and that's my limit in this case, negative 1 over 25. Okay, I think part J, limit t approaches 0, square root of t squared plus 9 minus 3 over t squared. Let's go ahead and plug the number in first. If I go ahead and plug in 0 in there, square root of 9, so that would leave me with 0 over 0, and that's not okay. We're not happy with 0 over 0. So what do we do now? We're going to limit t approaches 0. We're going to rationalize the numerator. T squared plus 9 minus 3 over t squared plus 9 plus 3, multiply with the conjugate. Okay, multiply the numerator and denominator with the conjugate. As long as you do multiply both numerator and denominator, you are okay, you're fine. All right, so let's see. Square root of t squared plus 9 minus 3. So go ahead and FOIL the numerators and the denominators. Actually, I'm not going to FOIL the denominators. I'm going to leave them like that. It might come handy for me to leave them without distributing. So I would be left with t squared plus 9 minus 9 divided by t squared times t squared plus 9 square root plus 3. Now, limit t approaches 0, t squared, square root of t squared plus 9 plus 3. Now, I have, the t was causing me trouble because when t was becoming 0, things were getting crazy with t becoming 0 for me in this case because I also had t in the denominator. And in the numerator, I was still getting 0 over 0 form, but with t being cancelled, I do have a remaining function which is continuous at t equals 0. So I can go ahead and plug in the t as 0. So 1 over 6 is my limit in this case. Okay, I'm leaving problem number 1 and 1, 2, and 3 for you to try. Go ahead, give them a try. The limit should be 2, the limit should be 3 here, and the limit should be 1/2. Give them a try on your own to see if you can handle these problems. There was one trick problem that we left here. So limit x approaches 0, cotangent x over cosecant x. So let's see. Sine of 0 is 0 and cosine of 0 is 1, right? And cotangent x is tangent is sine over cos, and cotangent is cosine over sine, right? Cosine over sine is cotangent. So this would be 1 over x is not equal to 0. X is getting really, really close to 0. So x is approaching 0. X is not equal to 0. So 1 over a very, 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 very small number, that would be infinity. And cosecant is 1 over sine x, which will be 1 over 0. Again, 1 over a very, very small number. X is not 0. X is approaching 0. So you can do 1 divided by 0.000005, and you'd get a really, really large number. So x is infinitesimally close to 0. X is not equal to 0. Okay, so this is also indeterminate form. So how do we handle this indeterminate form? We are going to, let's express them in terms of sine and cosine and see if we can simplify from there. Cotangent x is cos x over sine x, and we're dividing it with cosecant x, which is 1 over sine x. So again, cos x over sine x, the division will change into multiplication, and we'll flip the term on the right hand side, and this is going to leave me with, we can cancel the sine x and sine x. Limit x approaches 0, cosine of x is 1, and that's going to be our limit in this case. Okay, that will be the limit in this case. All right, so next we have, let's see, there's one more problem that we didn't touch yet. This one, x approaches 3, x squared plus x plus 1 over x minus 3. So what is happening in this case? Remember earlier we talked about, go ahead and do direct substitution. If you do direct substitution, what happens? If I plug a 3 in there, 3 squared plus 3 plus 1 over 0. That's what I'm getting, which is 3 squared is 9, 13 over 0. So if you get a number over 0, in the beginning we said if you get a number over 0, that means there is a number over 0. That means there is a vertical asymptote. So for this function, there is a vertical asymptote at 0.3. So vertical asymptote. How can you tell what is happening to the limit? So we would have to do limit x approaches 3 from the left hand side, limit x approaches 3 from the right hand side. For now, we can go ahead and do x squared plus x plus 1 over x minus 3, and same thing, x squared plus 1 over x minus 3. So we can think of x approaches 3 from the left hand side, so we can replace x by 2.99999 and see what happens. What do I get? Or when x is approaching 3 from the right hand side, we can replace x by 3.0001 and see what happens. What do I get? And you can also look at this graphically using Desmos. So x squared plus x